All right, so this is the video in which we're really getting into the thick of it. Um, at least, I don't know, maybe some of you love this stuff. Let me know in the comments. But for some of you who started watching with the easy explanation, the more down-to-earth explanation of She's at the beginning, maybe this is a lot. Um, well, okay. Today we're finally going to get to the beginning of limits and defining limits and what that means. And eventually in a video or two, we'll, come back down to earth and unpack that in the context of sheaves. So to that end, we're going to start a little bit abstract. I'm going to suppose that I have a category C, fancy C. That's my attempt at drawing like a math cal C. And another category J, which we're going to think of as, we're going to call it an index category. So you will see why a little bit in this video, but more so down the road, because often it really is just like indexing a collection of things. And I'm going to define for each object, for each object. So again, if I have a category, sometimes I write a little lower 0 to mean an object of that category, say this is the set, I guess. And uh, I'm going to define a functor from J, so the functor itself, it's going to be called delta sub J of C because its definition depends on C. So it's going to go from my category J to my category C. And what is it going to do? It's I need to tell you what it does on objects. So it's going to take an object and it's just going to send every single object to C, right? So it's somehow like a constant functor, right? It just sends everything to the same object. And I need to tell you what it does on morphisms. So what is it going to do on morphisms? Well, let's say I had a map from J to K. Well, I'm just going to send everything to the identity map on the object C, right? Because this functor sends both J and K to C. So I need to come up with some map to C. Well, it's got to be some map that I got it guaranteed to be here, right? Because both J and C are just abstract categories. Well, there's really only one map that I guarantee to exist. That's the identity, right? Okay. So now that we've done that, I claim that this process of sending objects C of my category to these functors delta sub J, I claim that itself is functorial. What do I mean by that? So recall that we have a notion of morphisms between functors, right? We actually saw that in our definition of a sheaf, right? Our definition of pre-sheaves were just functors. And when we unpacked the definition of a morphism of those pre-sheaves, that was exactly the data of a natural transformation. So I can form CJ, which kind of reflects the set theoretic notation, right? If you think about sets like A and B, this is a shorthand for the set of all functions from A to B, right? So C to the J is the category of all functors from C to J. And I claim that delta sub J, so I'm going to call this thing delta sub J. It goes from my category C to the category of functors from J into C. What does it do? Well, you might already guess from the notation. I'm going to send an object. Well, I already have this notation picked out, right? For exactly this reason. I'm going to send the object C to this functor delta sub j of c that I previously defined. Um, and well, I need to, if I have a morphism in my category C, and let's say I called that morphism, I have some notes on the board because I'm going to get confused with more diagrams, F. Well, what do I need to do? I need to somehow use F to produce a morphism in the target category, right? In C to the J, right? But that is a morphism of functors. So in particular, that had better be a natural transformation. So that means that for all, I'm going to call this U. So this is a map in the category J because I need to define a natural transformation between functors that go from J into C. I better have, uh, uh, let me make just a whole new screen here. So I'm going to make a big picture. Now this is going to look complicated at first. I swear it actually turns out to be really, really, really simple at the end of it. So here I have this object, right? I can apply my functor to this map U. Here's the functor applied to the other object K. Now I have a natural transformation down to here. dj applied this functor. I don't think I made this picture big enough for what I want to do. So let me put a question mark here, right? Because I'm trying to define my natural transformation. And this is delta JC at K. So I don't know what these maps are going to be, right? I want to pick them so that I get a commuting diagram. But let's unpack what all of this is. Delta J of C, right? I said that was going to be the constant functor, so that just sends everything to C. So my corners is just C, C, D, and D, right? And the map U is just the identity on C by definition. And this is the identity on D by definition. So I need to choose some maps from C to D that make this diagram commute. But remember how we started this whole thing, right? I was trying to convince you that this is a functor, right? And so that began with starting with a morphism in the domain category, but that's just a map from C to D. And so I could literally put that map in both places, right? So that's the natural transformation that I get. And so that's, so the outer diagram looks pretty complicated. It's actually, kind of redundant. Okay, big whoop. You might be like, where the hell are we going with this? So remember, the J is going to be some sort of index. Maybe I should just tell you now. That is that category for the one we're interested in. Well, how is this going to come up for sheaves? Well, think about it. A sheaf is a functor from one category to the other. The pre-sheaf is. And in the topological case that we care about, what is a sheaf? It's a functor from the category of open sets of a topological space into, let's say, abelian groups. Well, actually, it's contravariant, but let's just bury that for a second. So it's from open sets to abelian groups, right? So if we think about this notation, what is the J? Well, the J is playing the role is of the category of open sets, right? So somehow, right? And if we think about it, the sections of our sheaf are literally, they're indexed in some sense by open sets in our topological space, right? There's one of these corresponding to every U. So Okay, just I'll throw you a little bone in the wake of this massive abstraction here. So what do I want to tell you about next? Well, I want to tell you that if I have, we're gonna make use of this in a second. So there's a reason I'm spelling it out. So in general, I want to tell you what a morphism in this category looks like. So remember, these are both delta sub j of c and a. These are both functors from J into C. The delta J sub C is defined specifically, but I'm going to suppose that I've got like this arbitrary A. So what does that look like? Well, now I'm going to say, so again, that's a natural transformation. So for any morphism in the category J, what does that mean? That this means I've got a natural well, unpacking what it means to have a natural transformation. Again, let me just draw the whole, diagram, and as before, it will make, it seems complicated, but we're going to see that it's really just simplifies. Sorry, there should be, oh, what am I writing here? This is a J, right? We have this. Well, remember, again, I'm applying my functor delta sub J of C to this map F. It's going to send it to the identity at C, where both of these things, despite the fancy way I write them at first, this is just C, right? And then this is just like equality. So here we have phi sub k, a k, and over here is a of u, right? So really, I can sort of, because of this equality, I can just sort of squish the top two parts of the diagram together. And what does this really say? It really says that I have some maps phi j and phi k out of my object C down to these j and k in a way that's commutes with a of u in this compatible fashion, right? Okay, so that simplifies a little bit. And it's nice to have this simplified picture for the craziness we're going to do in a second. Okay. I'm going to be looking behind me a lot because I have a bunch of notes on the whiteboard behind me. What are we doing with all this? Well, so now we have what? We've got our functor. So hint, hint, it has something to do with the previous video. Suppose, so we have our functor, delta sub j, we call it the diagonal functor. What if this had an adjoint? What if this had an adjoint? Well, I'm going to call this adjoint the limit. So if this functor has a right adjoint, yes, if it has a right adjoint, then so delta j, I'm probably doing the turnstile the wrong way. If it has a right adjoint, then it's going to be the limit. By the way, guess what? If it had a left adjoint, those of you who have heard about limits in category theory before, it's going to be the co-limit, right? Shocking. And so last time, actually, we saw that in order to explain that there's an adjunction, it's actually enough to just tell you what the unit of the adjunction is. So suppose these functors are adjoint, and let's consider the unit of adjunction. So what is the unit of adjunction? It is a map. Well, it is a natural transformation, which is going to go through. Did I say unit? I want to describe the co-unit. Yeah. So I'm going to use an epsilon, and it's going to go from delta J composed with, oh, yeah, and did I write the wrong limit too? Sorry. This is, in order to be consistent with notation, sorry, this is the limit that goes this way. This is the limit where the arrow points this way. BT dubs, right. So I need a natural transformation from the composition of these two functors into the identity functor on the category C to the J. Okay, well, let's try and unpack what that means. Well, in particular, like moreover, not only is all of that stuff true, but I need it to be the case that for all maps from delta J at some C into A, which, by the way, this is a map of functors, so that's a natural transformation. There exists a unique psi going from the object C into the limit of A, such that what? Well, there's a unique psi so that the following diagram commutes. So if you recall the co-unit definition, the defining diagram, I'm just unpacking what that means in this context. So I have delta JC down to delta J of lim. And actually, I should be writing a little j underneath here, just so you know it's the limit adjoint to this thing. But of A, here's going to be my epsilon at A. Here is going to be delta J of psi. And here is going to be what? I should have A, and I should have my phi. Okay, so let's try and unpack what all of this says. Well, we have part of this already, right? So what does psi say? Well, the psi, remember, that's a natural transformation, and it just says that I have this diagram, right? What about epsilon sub A? Well, this using the same idea, right? I know this, right? This was me writing what happens when I have when I have a natural transformation from delta J of something into anything else. And then I just unpacked this diagram, right? So we're literally gonna copy it. Can I physically copy it? I can here. Can lasso it, but my mouse is giving me problems. Aha. Fantastic. So I've got that. And now I'm just going to unpack this for delta for this here, for this natural transformation with epsilon A. So what am I going to have? Well, I will have lim JA, right? This is playing the role of where my C is in this picture over here. And now I'm going to have some arrows going down to what? Well, that's just going to be to A, J, A, U, A, K, in a way that makes this commute, and I'll call this epsilon A, J, epsilon A, K, right? Okay, well, it seems like probably, I've got the same stuff on the bottom here. I've got the same stuff on the bottom here. I can probably squish these things together. And not only can I squish these things together, but remember, I want to talk about what the commuting of this diagram actually means? Well, let me try and squish these two things together first. So I have, let me draw it this way. So I've got A, J, and now I'm going to put this pointing down to AK, and here's A, U, right? So I've got that part. And let's use different colors for all of it. Let's do, so I'll put C here, and here's my phi j. Actually, I'm going to put that beneath. Doesn't really matter. Here's my phi j. Here is my phi k. And I've got over here lim, going backwards, j of a. And I've got my map, epsilon a j, and my map epsilon a k. And now what does the last part I haven't unpacked is this defining feature of it being a co-unit, right? So, psi seems like a green Greek symbol to me. I don't know if you feel the same way. Maybe it's black and blue, and I don't know if you feel synesthetic about symbols at all. But so I should have a unique map going between these things. And so there's a unique map psi. But actually, that psi is supposed to do something else, right? It's after I compose, after I compose and apply this. Well, remember, this was just some going back to our diagram up here. Remember that, so now this is what our psi is, right? It's just some map from C to D, but now in our picture, it's just a map from C to A that makes this diagram commute. So that's actually not really saying a whole lot, right? I mean, every map from C to A will make this diagram commute, right? But so in particular, though, it's the fact that there's a unique map here. And now, I think that's the end of all the notes that I had. But now we see that this defines, maybe if you've seen something like a limit before, this is probably closer to that definition of a limit you've seen, right? So so let me say this. So the way I unpacked it is I started by talking about, I said that the limit is going to exist if, what did I say here? If I have an adjoint to my diagonal functor, right? And then what we did is we unpacked what that meant in terms of having a co-unit, right? And unpacking that basically gave us this familiar picture. And I claim that we can go the other way. So what I mean by this is a diagram, you have limits. We call them limits of shape J, and we'll see why in a moment. Will I give an example at the end of this video? Maybe in the next video. I don't know. I'll give one in this video probably. So if we have a limit of shape J, what that means is there exists some object that we normally call by this, such that for any object that has maps making this triangle commute. So I should slow down. There's right. A limit of shape J is an object together with maps making this diagram commute, such that for any other object C with maps making this other diagram commute, there exists a unique map from C into this thing, right? So that's when we say this object, which is a limit, exists. Okay. But in particular, let's think about what it means if we had that definition, right? So we got there from unpacking the co-unit definition. Suppose that was true for the co-unit definition, right? Well, I claim that having this diagram also just conversely gives us the co-unit, right? Because what did we need to do? We needed to construct, right? In order to make it true, we needed to construct a unique psi, which was actually a natural transformation between these two things that did some such stuff. But remember, so if we have this diagram and that psi exists, then I can define a natural transformation just in this way. Great. So I get that natural transformation, and then I simply claim that well, you can check that it will make this diagram commute when you simply unpack it again and come back to the shape. Okay, that was a messy explanation, I think, at the very end. But let me say this because you also might be wondering, well, what does this have to do with like limits in calculus or limits in topology? We oftentimes think about so J is an index just like an index in a sequence, except now, we somehow get algebraic objects. And it's somehow like if you have a sequence of algebraic objects, converging to something. So I swear I'm going to write my arrows wrong, but maybe this is one I'll touch on in a future video. But for example, if you take the limit over p to the n over all n in n here, right? What do you get? Well, you get the so-called p-adic integers. I don't mean the integers mod p when I write this. I always write my integers mod p like this. And why is it? Because you can sort of think about it as this actual like limit of algebraic stuff, right? Like if you have so there's more information here than I'm skipping, right? But like if you have the integers mod p to the n plus 1, you get a map to the integers mod pn by just quotienting by pn, right? Like this surjects onto here, and then you can also you can go back even further along the sequence, and you can go back further in a compatible way, and you can sort of imagine like as you're taking these bigger and bigger quotients, you're somehow getting this larger and larger object, and you might wonder if that somehow runs into some ultimate final algebraic object that actually exists, and that's what the limit is allowing you to do. Okay. Maybe just quickly one example, which is actually abstract. If we think about let J be the discrete category, so it's just going to be the category with two points, I don't know, A and B, and no other morphisms except so the axioms of a category demand that, I need to have identity morphisms, but that's it. So this entirely specifies my category. And what would it mean? So if we think about this diagram up above, what would it mean for this thing to have a limit? Well, here there's no if I take like J is my A and K is my B, well, there's no even maps between these two things, so there's nothing to worry about there. So I just have this A and B. I have this thing which is like my limit of this shape of some functor. I shouldn't call that a, bad notation. Let me write F for some functor. Going into A and B, right? And what am I saying? If we look at this diagram, it says, well, if I have any other thing C that has, and so remember the conditions has to make the diagram commute, but well, there's nothing to say, right? But it says if I have any other C with maps into here, then there has to exist a unique morphism that makes this diagram commute. But those of you who have seen some category theory before will recognize this as the universal property defining the product. Right? So there's all these instances like you can take the Cartesian product of sets. You can take the Cartesian product of topological spaces. You can take the direct sum of two groups. You can take a direct sum of modules and so on and so on and so on and so on. There's all of these different definitions of products in a category, and this abstract way of writing them is all captured. So that's a very special case of a very certain limit for this kind of stupid choice of J. Okay, that's where I'm going to leave it. I could explain this product thing more. Maybe if you ask me nicely, I will. But I think at this point, we're now, I'm going to, in the next video, which who knows when that will be, start getting back to sheaves and exploring how we recover the definition of stocks that we know and love and realize it as this limit concept. So I'll see you in that one.